Have you ever stopped to think about what's really going on inside your computer? I mean, we type, we click, and things just happen. But it's not magic. Not at all. It's actually a super logical process. Today, we're going to peel back the curtain and follow one single command on its incredible trip deep inside the machine. Okay, let's just dive right in. It all starts with something that looks super simple, right? A line of code, like z equals x plus y. We're just telling the computer, hey, add these two numbers. But to the computer's actual hardware, that's a completely foreign language. So how does this thought that we can read turn into an action the machine can take? That's the big question we're tackling. So here's our game plan. First, we'll see how our code gets translated into a language the machine can actually understand. Then, we're going to go right inside the computer's brain, the CPU, to see our command live out its life. And finally, we'll uncover the secrets that make all of this happen at just mind-boggling speed. First stop, translation. That little line of code, z equals x plus y, makes perfect sense to us. But to the processor, it's gibberish. Total nonsense. So, before anything can happen, it has to be converted into the only language the hardware speaks, the language of ones and zeros, binary. This whole translation thing happens thanks to a really important program called a compiler. The compiler's job is to take our high-level code, the stuff written for humans, and break it down into a series of low-level machine instructions. And these instructions are just pure binary code, a long string of ones and zeros that the processor can finally understand. So what exactly is an instruction? Well, think of it like a complete bite-sized command. It's a chunk of binary code that tells the processor two super important things. First, what to do, like add, and second, what to do it with. In our case, the numbers that are stored in X and Y. So who gets these binary instructions? That brings us to the star of our show, the Central Processing Unit, or CPU. This is the honest-to-goodness brain of the computer. It's where all the thinking, all the calculating, and all the order following actually happens. Now, inside the CPU, you've got this little dream team working together. There are three key players we need to meet: the control unit, the arithmetic logic unit, and a bunch of super fast memory spots called registers. Each one has a really specific job to do. First up, the control unit, or CU. This is the orchestra conductor. It's the boss. It doesn't do the math itself, but it tells everyone else what to do. It fetches the instructions, figures out what they mean, and then coordinates the whole show. It's the project manager of the CPU. Next is the arithmetic logic unit, the ALU. This is the math whiz, the number cruncher. When the control unit gives the order to do some math, like our addition problem, it sends the numbers over to the ALU. This is the part that actually does all the binary calculations, adding, subtracting, you name it. And finally, we have registers. The best way to think about these is as the CPU's personal scratch pad. You know when you're doing a tough math problem, you write down numbers in the margin to keep track? That's what registers are. They're tiny, extremely fast storage spots right on the CPU chip itself, holding whatever data it's working on at that very moment. Okay, so we've got our binary instruction, and we've met the team inside the CPU. Now let's put it all together and see what actually happens when our command gets its moment in the spotlight. The CPU is running a constant repeating cycle for every single instruction it gets. This is it. This is the heartbeats of your computer. Fetch, decode, and executes. That's the rhythm. Every single thing your computer does, from moving the mouse to playing a video, is just the CPU doing this three-step dance, billions of times a second. Okay, let's follow our z equals x plus y command. First up, the fetch phase. The control unit reaches out to the computer's memory and grabs the next instruction in line, in our case, the binary code for add, and pulls it into one of its registers. Next up, decode. Now the control unit looks at the binary code it just fetched. It deciphers the pattern of ones and zeros and figures out what it's being asked to do. It recognizes the code for add, and it sees that it's going to need the values of x and y to get the job done. And finally, the execute phase. This is showtime. The control unit, knowing exactly what to do, grabs the values for x and y, sends them over to the ALU, and says, go. The ALU does the addition, and the control unit makes sure that result gets stored in the right place for z. And just like that, our command is complete. Now, I know what you might be thinking. That sounds like a lot of steps for just one addition. And getting stuff from the computer's main memory, the RAM, is actually pretty slow compared to how fast the CPU is. So what gives? How are computers so incredibly fast if the CPU is always waiting around? Well, the secret lies in a really cool idea called the principle of locality. It's a fancy name for something pretty simple. Computer programs are predictable. They don't just grab data from random places, they tend to reuse the same small bits of data over and over, or they access data in a nice, neat sequence. And to take advantage of that predictability, computers use a clever trick called a memory hierarchy. Instead of just having the super fast CPU and slow main memory, there are layers. You have the registers right on the chip. That's the fastest. Then right next to it, a small, very fast memory called cache. Then the bigger, slower RAM, and finally, your slowest long-term storage like a hard drive. And that cache memory is the real hero here. Because programs are so predictable, the computer can make a really good guess about what data the CPU is going to ask for next. So it proactively copies that data from the slow RAM into the super fast cache. That way, when the CPU needs it, boom, it's right there, no waiting required. So with all this working together, just how fast are we talking? Well, you see a number on the box of a new processor, something like 4 gigahertz. We see that number all the time, but what does it actually mean, based on what we've just learned? Get ready for this. It means that whole fetch, decode, execute cycle we just walked through. The computer can do it 4 billion times, every single second. It's absolutely staggering, and it's all thanks to that clever memory setup and the raw speed of the processor. You know, the most amazing thing is that this fundamental idea, this fetch, decode, execute cycle, has been the heartbeat of computing for over 75 years. It was there in the giant room-sized machines, and it's right here in the phone in your pocket. It really makes you wonder, what's next? What will the fundamental cycle of computing look like 75 years from now? Thanks for watching.